Hello, welcome to our video notes on Newton's second law, part of our forces unit. In some of the last videos, we talked about Newton's first law, which is the idea that a body at rest will remain at rest unless acted upon by an outside force, and a body in motion will remain in motion unless acted upon by an outside force. Newton's first law and Newton's second law ultimately kind of say the same thing. Today we're going to look at what Newton's second law actually says. Now, from our notes and activities on net force and equilibrium, we know that if the net force is non-zero, if it's not zero, then what that causes is for objects to accelerate. And accelerate just means that they are changing their velocity. Notice that it doesn't just cause objects to move. It causes a non-zero net force causes objects to change their velocity. Okay, there's a difference between just causing motion and causing an acceleration. Non-zero net forces cause an acceleration. So we have this relationship between forces and accelerations, and it turns out that they are proportional to one another. In other words, applying a bigger force to a certain object leads to a bigger acceleration, and it works the other way as well. Applying a smaller force leads to a smaller acceleration. So whenever we see things that are proportional or seem like they're proportional, we often want to know, well, how can we make this into an equality? How can we make this into an equation? Is there a direct way to calculate if this is the acceleration, then this is the force, or vice versa? If this is the force, then this is the acceleration. Well, it turns out that there is. Exactly how much acceleration results from a certain force depends on an object's mass. In fact, if we know the mass of an object, that allows us to write an equation relating those three quantities. And the equation, as is being said by our fabulous Isaac Newton right here, is F net equals m times a. The net force equals the mass times the acceleration. This is Newton's second law. This is probably the easiest one of Newton's laws to remember, simply because it's an equation. Okay? It's a very simple, very short equation, but it's probably the most powerful equation that we will learn this year. Newton's second law simply says that the net force on an object is equal to the object's mass multiplied by its acceleration. And I said it kind of relates back to Newton's first law, which is an object will continue doing whatever it's doing unless a net force acts upon it, because F net is the net force that acts upon it. If there's a non-zero net force, then A must be non-zero. Why is that? Think about any object that you know. Any object that we list has to have some mass. It has some matter to it. So any object that we have must have a mass. If the net force is zero and mass is not zero, well, there's only one option for the acceleration to be then. It must be zero, because anything times zero is zero. It doesn't matter what the mass is. If the net force is zero, the mass could be 100 trillion kilograms. The acceleration is zero. If the net force is non-zero, we know that m is non-zero. A must also be non-zero. So the presence of a net force will cause a non-zero acceleration, which means that the velocity will change. Or if you want to think of it this way, it means the motion will change. That's why it relates back to Newton's first law. Now, we can rearrange this formula into two other equally helpful formulas in case you want to solve directly for one of these variables. If I simply divide both sides by A, I get m equals F net over A. And probably more importantly, because this is how it's written on the reference tables, if I divide both sides by m, I get A equals F net over m. And this is what is in the reference tables. Okay? Usually we end up writing it like this, but this is the way it's written in the reference tables. And I think the reason it's written like that in the reference tables is because net forces cause accelerations. It's not the other way around. The acceleration is a product of the net force. Based on all the forces, an object will or will not accelerate. It's not that based on the acceleration, the object will have this net force on it. So it's a little bit of cause and effect there. Let me go get a reference table. So just so you can see exactly where this is on the reference table, it's on the back in the mechanics section. Right under the equations for sine and cosine, the y and x components, we have a equals f net over m, about 1/3 of the way down the reference tables. So a couple of notes before we get to the examples. This equation only works if you know the net force. One of the mistakes that I see people making is they try to use this equation with just any force, okay? Maybe a force of gravity, or maybe a force from the ground, or someone pushing on the object. Now, it might turn out that those forces are equal to the net force, but that's not going to be true all the time. You must find the net force, the sum of the forces, before we can use this equation, F net equals ma, or at least you must write it that way. Okay, it's not any force, it's the net force, the sum of all the forces. Now, at the very end of the kinematics unit, we started dealing with two-dimensional motion, motion in the x direction and y direction. And we had to split up our variables and talk separately about those directions because they had no effect on one another. That's the same here. If you're dealing with two-dimensional motion, you can use this equation to find the acceleration or net force in either the x direction or the y direction. They don't have to be equal, and they're not going to affect one another. They are separate. So in a lot of cases, we're going to write net force equations for both the x direction and the y direction. Okay, we treat them completely separately. Let's talk a little bit about the units. We know that the units of force are newtons. We've known that for a few videos now. But what is a newton? Okay, it's very easy to visualize a meter or a kilogram or a second. What the heck is a newton? Well, let's look at the equation we just learned. F net equals ma. Now, someone came up with the idea a long time ago that the units on one side of the equation have to equal the units on the other side of the equation. Otherwise, it wouldn't make sense. We'd be comparing completely different things. Okay? The units have to be equal. So here's what I'm going to do. The units on the left-hand side we know are going to be newtons. Those are the units of force. And I'm going to write this in brackets because that's the standard way that you identify that, hey, we're just talking about units right here. Brackets mean that we're looking at the equation's units. Okay, so on the left-hand side, we have units of newtons. On the right-hand side, we have mass times acceleration. Well, what are the units of mass? Mass is measured, as we know, in kilograms, and acceleration is measured, as we know, in units of meters per second squared. So what this leads to is that if the left-hand side units must be the same as the right-hand side units, then 1 newton, imagine this kilogram is over 1, and then we multiply the fractions, 1 newton is equal to a kilogram times a meter over seconds squared. An equivalent way to write the units for force, again, is 1 newton equals 1 kilogram times a meter over a second squared. Now, does that mean anything to you? No, and it probably shouldn't. It's just a random jumble of units. But those are the equivalent units for a newton. You will be asked this multiple times, and on a few of some of the upcoming units, you'll also be asked to remember what some other units are equal to. But anyways, you need to know that a newton is equal to a kilogram times a meter over a second squared. It seems to come up a lot, not only on my own stuff, but also on the actual Regents exam. Again, like I said, many of the next topics we will discuss have their own units that can be broken down into more fundamental units. Force is the first one of these. So this is an important thing to remember. It's a it's a memorization. You can recall it very easily. If you don't remember it, just remember how we got there. We looked at the equation. We said that the units have to be the same on each side of the equation. And then we just plugged in our units, and we solved for what a newton was equal to on the other side of the equation. Very simple. Now, let's get to some examples with Newton's second law. Okay, we're about to start using one of the most powerful physics equations that you're going to learn. So it's very versatile and it's very important. Example. An object with a mass of 2 kilograms accelerates at a rate of 0.4 meters per second squared. What is the net force on the object? Well, We're told the mass, 2 kilograms. We're told the acceleration, 0.4 meters per second squared. We're looking for F net. We write our equation. We plug in our units, 2 kilograms times 0.4 meters per second squared. .8 newtons is the net force. We know that because it's a 2 kilogram object. It accelerates at a rate of 0.4 meters per second squared. We just got to multiply those. Let's look at another version. A 20 kilogram object experiences a net force of 50 newtons. What is its acceleration? We know the mass. We know the net force. We're looking for the acceleration. Now, I'm going to keep using this. You could use one of the rearrangements that directly solves for A, but I'm going to do this. The net force is 50 newtons. The mass is 20 kilograms, and we're looking for A. We divide both sides by 20. 50 divided by 20 is 2.5 meters per second squared. Based on that net force and that mass, we can solve for the acceleration. Okay, very simple. If a net force of 124 newtons causes an object to accelerate at 0.77 meters per second squared, what is the mass of the object? F net equals ma. F net is 124 newtons. The mass is what we're looking for. The acceleration is 0.77 meters per second squared. The mass ends up being 161.04 kilograms. Based on that net force and that acceleration, that's what the mass must be. Now, these are the easiest possible net force problems. What makes it harder is when you don't know the net force at first and you have to solve for it in order to find the acceleration. Let's look at one of those problems. A 20 kilogram box is pushed to the right with a force of 50 newtons. The force of friction on the box is 35 newtons. What is the box's acceleration? So in this case, we know the mass. We have a force, there's a box that's getting pushed. I don't know, maybe I'll call that the force push, F push. And then the force of friction on the box is 35 newtons. I'm going to label that F. And we're looking for the acceleration. I know the mass, and I know I want to find the acceleration, but I don't know the net force. If you get to a problem like this, where it's not just a simple one-step plug into the equation and solve solution, and you know it's a forces problem, what you should automatically jump to is drawing a free body diagram and writing out net force equations immediately. Okay? So, for this box, I'm going to label this box. I'm going to put an axis. Okay? And I'm going to label the forces that are on the box. Now, let's label all of them. I know that the box probably has a force of gravity on it, so I'm going to draw that down. And I'm going to say force of gravity. I know that there's a force upwards from the surface the box is on, so I'm going to write force from the ground. And I know that to the right, let's see, there's a force called F push. And I know that's larger than the force of friction. Friction opposes motion. Let's assume the box is moving to the right. So let's assume that friction points back to the left. F. Now we want the box's acceleration. And it's kind of implied we want the box's acceleration in the x direction, in the direction that we're pushing on the box. So even though I'm only looking for the acceleration in that direction, I'm going to write out my net force equations in both directions. I'm going to do the y direction first. F net y equals F ground. I know that that is a positive force because it's in the positive y direction because I made my axis that way. I could have just as easily made it with with down being the positive y direction. Minus the force of gravity. Again, that's the force on the box from the earth. Now, this is all familiar to us, but we just learned that a net force is equal to mass times acceleration. So I have three different things that I'm going to write here. The net force, here's the sum of my forces. I'm going to put another equal sign and say that this is all equal to m times the acceleration in the y direction, since I'm looking at the net force in the y direction. Okay? It might look weird to you to have two equal signs right here, but all we're saying is that all of these are equal to each other. The net force is equal to m times ay, which is equal to the sum of the forces in the y direction. Now, in the y direction, it doesn't say anything about the box moving down or moving up, accelerating downwards or upwards. Matter of fact, we can probably assume this box is on a flat surface, in which case it's not suddenly going to just sink into that surface, and it's not suddenly just going to rise up off of that surface. I think we can pretty safely assume that this box is going to remain on the surface. And if that's true, then the velocity of the box in the y direction is 0, and it's remaining that way. If you can come to that conclusion, then we know that there must be no acceleration in the y direction. So we cross that off and say that it's equal to 0. And if I cover this up and say that this minus this equals 0, then look what I can do. If I add gravity over to the other side, I have just concluded that the force upward from the ground must be equal to the downward force of gravity, causing a net force and an acceleration of 0. If this is 0, if the acceleration is 0, then that means the net force is 0, which means the sum of these two must be 0. Since they're in opposite directions and the sum is 0, that must mean they have equal magnitudes. You're going to get used to this reasoning because we use it a lot. Let's talk about the x direction. That's the direction we really care about in this case. F net x equals F push minus FF equals MAX. We're solving for the box's acceleration. Now, you might be like, well, hold on, I only know the force from the push and the force of friction. I don't know what F naught x is. Well, we're only going to use the parts of the equation that are useful to us. And what I mean by that is we're only going to plug in for what we need to. Even though we don't know exactly what the net force is, we could find that very easily. We know F push minus FF must be equal to the net force. But I'm not even looking for the net force. Why bother solving for it? I know that F push minus FF equals MAX. So here's what I'm going to do. I'm going to plug in for the force from the push, 50 newtons. I'm not even going to write the net force part again because I don't care about that. It's not something that I'm necessarily looking for. I could find it if I want to. I'm going to plug in for the force of friction, minus 35 newtons. And I'm going to plug in for the mass of the box, 20 kilograms. And this is all, okay, and then we're multiplying that by AX. Now, I'm going to do some math. 50 minus 35, 50 minus 35 is 15. So I have 15 on this side. I divide that by 20. I divide the 20 over to the other side, and that's AX. Notice that 15, therefore, must be the net force. Again, I'm not going to solve for that directly because I'm not asked to. In any case, 15 divided by 20 means that the acceleration here is 0.75 meters per second. Now, what does that mean? Based on the net force, based on the size of these forces, the object is accelerating at a rate of 0.75 meters per second squared in the x direction. Is it the positive or negative x direction? Well, we said that the positive force was the force from the push, and we plugged that in as a positive number. Our acceleration is also positive, so that means that the acceleration must be in the same direction as F push. In other words, to the right, where x is positive. Okay? That's how that works. I'm going to stop there, and we're going to do the last 4 examples in a separate video, but that gives you a little taste of how to properly use a free body diagram and a net force equation and combine that with what we know about the net force now, that it's equal to m times a. Again, when we come back, we'll do the last 4 examples.